Hey everyone, and welcome back. Today, we've got a seriously cool explainer lined up for all you focused learners out there. We're diving deep into the brilliant CS29 notes from Amon's AI journal, specifically looking at a truly fascinating algorithm, locally weighted linear regression. If you've ever wrestled with data that simply refuses to fit nicely onto a straight line, you are going to absolutely love this. We're going to break down the complex math, look at the brilliant engineering trade-offs, and see exactly how this algorithm works under the hood.
So here's our roadmap for today. We'll hit the feature dilemma, look at locally weighted regression, dive into the weighting function, figure out how to tune the bandwidth, and wrap up with parametric versus non-parametric models.
All right, Section 1, the feature selection dilemma, choosing the right fit.
Picture this. You've got a dataset. Let's go with a classic, housing prices based on square footage. The absolute first thing you got to ask yourself when fitting a model to this is, what features are we actually going to use? I mean, this is the jumping off point. Whatever you choose here is going to dictate the whole rest of the process.
Usually with standard linear regression, you're stuck manually picking and stringing together different input features. And if your data isn't just a neat straight line, well, a simple straight line fit isn't going to cut it. You might have to try a quadratic fit, toss in a squared term. Or maybe you have to get totally custom and manually define new features with square roots or logarithms. It's basically a giant guessing game. You're constantly asking which combo of functions is actually going to capture the real shape of this data. And honestly, it can be a super tedious trial and error headache.
And this right here is exactly why that manual process is so tricky. Pick too few features, or the wrong ones, and boom, you get underfitting. Your straight line is just totally oblivious to the actual structure of the data. Now, you might think, okay, easy fix, I'll just throw a million features at it. More is better, right? Actually, no way. If you force a fifth-order polynomial onto your data, sure, the curve might magically hit every single training point perfectly, but that's overfitting. You end up with this wild, jagged roller coaster of a line that's going to be completely useless for predicting any new housing prices. So trying to brute force a good fit with way too many features, yeah, that's a really dangerous game.
Which brings us to Section 2, Locally Weighted Regression, a local approach.
Enter the real star of today's explainer. Assuming you've got enough training data, Locally Weighted Linear Regression, or LWLR for short, takes standard linear regression and tweaks it to handle nonlinear data like an absolute champ. It uses this brilliantly simple three-step process to make a prediction for any specific query point. Step 1. Instead of looking at the entire ocean of data all at once, it zooms in on the local neighborhood, just the training examples sitting right near your query point. Step 2. It completely focuses on those close neighbors and fits a straight line right through them. And Step 3. It simply makes the prediction based on that localized line.
So how does that actually look in math? Well, in standard linear regression, you minimize a cost function that treats every single data point exactly the same. But to make LWLR work, we use a modified cost function. We add in this weighting term, which we call WI. And its only job is to tell the algorithm exactly how much attention it should pay to each specific training example when it's fitting that line. It basically rolls out the red carpet for the data points closest to our query point.
Moving on to Section 3, the weighting function. Think of it as the algorithm's spotlight.
Now, there's a specific exponential formula behind the spotlight. But hey, don't let the math scare you. When you really look at it, it just boils down to a super simple, totally intuitive rule about distance. In this equation, the x without the subscript is the input we actually want to predict, and the xi is a specific training example.
The whole magic of this formula relies on one crucial property. It's basically an attention mechanism. If the distance between a training example and your query point is tiny, the mouth spits out a weight of pretty much exactly 1. So the algorithm multiplies the error by 1, meaning it pays a massive amount of attention to it. But on the flip side, if the training example is way far away, the math evaluates to a tiny fraction, pretty much 0. It multiplies the error by 0, which literally erases it from the equation. It completely ignores it. So that squared error summation, it's really only happening over the points right next door to where you're trying to predict.
Actually, let's pause for a second because I want to bust a little myth that Amon's notes call out perfectly. When you plot that weighting formula, the curve looks exactly like a classic Gaussian bell curve, right? The samples closest to your query point sit right at the top of that peak, getting the maximum weight. But the notes are super clear on this. These weights are not random variables, and they have literally nothing to do with actual Gaussian distributions. It just happens to look like a bell. A real Gaussian probability density function mathematically has to integrate to 1. This weighting function, it doesn't. It's totally just a cosmetic resemblance, nothing more.
All right, Section 4, tuning the bandwidth, controlling the window.
So we have a dial we can turn, a hyperparameter known as the bandwidth parameter. We represent it with the Greek letter tau. Tau is what dictates the exact width of that neighborhood we look into. It controls how drastically a training example's weight drops off as it gets further away from the query point. By messing with tau, you're literally deciding if your bell-shaped curve is going to be fat, looking at a really wide window of data, or super thin, zooming in on a very narrow window.
And you can see why tuning tau is absolutely crucial. Remember that whole underfitting versus overfitting headache we talked about earlier? Well, tau is steering the ship on that. If you set your tau way too broad, your curve is too fat. It looks at too many examples, oversmooths all the data, and boom, you're right back to underfitting. But if your tau is too thin, the curve fits the local data a little too obsessively, giving you a jagged, messy line that completely overfits. Dialing in that perfect tau is exactly what makes this algorithm sing.
Finally, Section 5, Parametric versus Non-Parametric. Let's talk memory and scaling.
Here is the ultimate catch, and it all comes down to memory. Regular old linear regression is a parametric algorithm, meaning once you train it and find your set of fixed parameters, those theta values, those parameters literally summarize the whole dataset. You could basically delete the original training data off your hard drive entirely and still make flawless predictions. But LWLR? It's a non-parametric algorithm. Because it relies on checking the local neighborhood for every single prediction, you have to keep all of the original training data loaded in your computer's memory, always. The storage you need grows right alongside the size of your training set.
As you can guess, that creates some massive computational roadblocks. LWLR is totally amazing if you're dealing with relatively low-dimensional datasets, say just 2 or 3 features. If your dataset is only a few thousand examples, the math is totally manageable and it runs super fast. But what if you scale up to tens of millions of examples? The math needed to calculate all that becomes an absolute beast. You actually end up having to use crazy scaling algorithms, like KD trees, just to get the thing to run. So yeah, non-parametric algorithms are definitely not your go-to for massive datasets, simply because they eat up so much disk memory. So that leaves us with a pretty big question to chew on. Is the incredible, flexible accuracy of non-parametric algorithms like locally weighted linear regression actually worth the massive memory and computational cost? I mean, sure, it completely bypasses the nightmare of manually guessing features, but it's going to demand some serious hardware to do it. It's the ultimate computer science trade-off, and knowing exactly when to deploy which tool, well, that's what separates the good engineers from the great ones. Thanks so much for hanging out with me on this deep dive through Ottoman's AI journal notes. I really hope this explainer made the brilliant mechanics of nonlinear data fitting a bit clearer for you. Keep exploring, and we'll catch you in the next one.